There's an invisible battle happening inside our electrical systems pretty much all the time. It's a kind of hidden chaos that can really mess with our equipment and just waste energy. Today, we're going to pull back the curtain on this phenomenon, something called electrical harmonics.
Okay, so let's get right to it. Over on the left, that's the dream. It's a perfect smooth wave of clean power, exactly how our grid was designed to work. But on the right, yeah, that's the reality in a ton of modern buildings. It's a distorted, jagged mess. And that, right there, is the problem of harmonics in a nutshell.
But to really get a handle on the chaos, we first have to appreciate the order, and that all starts with understanding what a perfect electrical wave looks like.
So this is what we call a sinusoidal wave, or just a sine wave. The best way to think of it is like the perfect heartbeat of our electrical system. It's this super smooth, predictable rhythm where the electricity flows back and forth exactly 60 times every single second. This rhythm, it's the foundation of, well, pretty much our entire power grid.
Okay, so we've got this perfect 60 times a second rhythm. But what happens when that rhythm gets invaded by other, conflicting signals? Well, that's when you get harmonics.
Here's a great way to think about it. A clean electrical wave is like one single pure note from a guitar. Harmonics are like a bunch of other notes trying to play at the exact same time. Now in music, that can create a beautiful chord, right? But in an electrical system, it just creates discord, a total jumble of chaotic signals.
So what this really means is, instead of the current moving smoothly at 60 times a second, you now have parts of it trying to vibrate at 180 times a second, 300 times a second, maybe even more. And all of these conflicting instructions are happening at the same time in the same wire. It's a mess.
And this shows you exactly how that mess gets made. You start with your clean, fundamental 60 Hz wave. Simple enough. Then you layer another frequency on top of it, say the third harmonic, which is vibrating 3 times faster. And what you get when you add them together is a completely new waveform. It's not smooth anymore, it's jagged, it's chaotic.
So you might be thinking, okay, a jagged wave, who cares? Well, this messy waveform isn't just some technical thing for engineers to worry about. It has real, tangible, and often very expensive consequences for everything plugged into the wall.
And this is where the rubber really meets the road. This electrical discord causes a whole host of problems. We're talking about wires dangerously overheating, transformers failing way before they should, and circuit breakers tripping all the time for what seems like no reason. And for your sensitive electronics, it can mean constant malfunctions, data loss, and random resets. It all adds up to wasted energy and some seriously expensive repairs.
That's the key question, though, isn't it? How does a messy electrical signal actually make a solid piece of copper wire get hot enough to melt the insulation right off of it? Well, the answer really comes down to efficiency. See, with a smooth sine wave, trillions of electrons flow back and forth pretty easily. But when you add harmonics, they're getting jerked around, trying to move forward while also being pulled in other directions. All that erratic, stop-and-go motion creates a kind of electrical friction inside the wire. And just like rubbing your hands together, that friction generates a ton of excess heat.
All right, so if this is the problem, who are the culprits? What's actually causing all this chaos in our electrical systems in the first place?
It turns out the culprits are all around us. They're called nonlinear loads. Basically, it's any modern electronic device that doesn't draw power in a smooth, continuous wave, but instead takes it in these little rapid gulps. So anything that converts AC power to DC and back again, we're talking motor drives, modern LED lighting, computer power supplies, even EV chargers. They're all constantly switching the power on and off thousands of times a second, and that injects these distorting harmonics right back into the system.
Okay, so it sounds pretty bad, right? But the good news is we're not helpless here. While we can't just get rid of harmonics completely, electrical engineers have come up with some really clever ways to manage and contain the chaos. It really boils down to two main strategies. The first approach is to actively filter out the chaos, basically using devices that clean up and smooth out the electrical signal. The second approach is to just build the system to be tough enough to withstand the chaos, using more robust components that can take the extra heat and stress without breaking.
So let's break that down a bit. Filters and things called line reactors, they basically act like shock absorbers for your electricity. On the other hand, oversizing a neutral wire is kind of like installing a bigger drain pipe so it can handle more flow without getting clogged up. And K-rated transformers? Well, they're just heavy-duty versions, built with more robust materials specifically to absorb and get rid of all that extra heat from harmonics so they don't fail. And this all leaves us with one final, and I think pretty crucial thought. Our world is becoming more and more dependent on the very electronics that create this problem, from the EV charger in your garage to the big inverters used in solar and wind farms. So the question really isn't if we'll have harmonics. The question is our electrical infrastructure truly ready to handle all this hidden chaos?